Hi, please sit down and let's start the new. Okay, just. Tudom, csak hallg, egy, kettő. Egy. Nincs. Ja, okay. Please. Nem szoktam mikrofonba kiállni, azért van a mikrofon, hogy ne kelljen kiabálni, nem? Okay, so let's start the new session. Our first speaker is Gergely László Nagy, who is at University, the Faculty of Informatics, and he's going to speak about real-time sensor data recording and processing for autonomous vehicle. Thank you.
Thank you. So hello everyone, my name is Gergely László Nagy, and today I would like to show you our research groups, the geometric computer vision groups, real-time data processing system. First, about the motivation. Our group collected a lot of data over the years, and we usually use it for offline applications, offline algorithms, but we wanted to use it for real time as well. So we try to develop and then publish to others system, a client-server architecture system, where the server puts the data, what it reads or comes from the vehicle directly to the named shared memory, and the client reads it out. The server uses double buffering for this, so and the flag. So the flag indicates which one can be read. So about the data, we have currently this sensor kit mounted to the vehicle. It has 4 pinhole cameras and one 3D LiDAR and an RTK GPS currently. And we collect data from it in real time with 4 samples per second. This is a compromise because we said that if some algorithm runs with 4 FPS, then it's great enough for real time for us. And with this sensor configuration alone, we have 800 minutes of footage recorded in Budapest. And we also have, besides the sensor data, the calibration data, intrinsic parameters for the cameras like focal length and focal point, and extrinsic parameters between the LiDAR and each camera. This is 3D rotation and translation each. And camera calibrations, also rotation and translation between neighboring pairs. And these were calibrated with the chessboard-based method. As you can see here, the points on the chessboard projected to the chessboard is blue, the others is orange. So about the client, I would like to talk about this. This is how it looks. It displays every data and visualizes it. And it was written with OpenGL and SDL2. We chose this because it's easier to port theoretically between Linux and Windows. You have just to replace the shared memory processing class because we use the Windows API for this currently. And the features, we stitch the cameras, the images together in a panorama orientation. And on the bottom, we display the point clouds and we color it with multiple color schemes and we draw the map around it. So first, we use this stitching to display the field of vision better. We use plane-plane homography for this. This is basically a perspective transformation between the images because we can look at them as planes. And for this, we have to assume that the translation, there is no translation between the cameras. That is not the case, unfortunately, but it's negligible, so we can omit it. And we get a good enough approximation for the final panorama image. There will be some parallax error, but it's good enough to show what we wanted to show. So for the existence, if we calculate the homography between each neighboring camera pairs, and we fix the origin to the first camera's focal point. And if we do this, then there will be only a rotation for each camera, represented by R1 and R2 matrices, and the intrinsic camera matrices like K1 and K2. And you can represent the 3x4 projection matrix, which projects the 3D point to the image, and these coordinates are represented in homogeneous coordinates as it is a perspective projection. And you can write this matrix, which will be the homography, what we are trying to find, in this case, between two image points. So we need to match these points on the images. And we do this on the CPU because we assume that the orientation of the cameras won't change over time because it's a fixed configuration. And we use a serve detector to detect key points. Then we match them with a Flam-based matcher. And then we estimate the homography. For this, we select 4 points, then find an initial estimation that minimizes an algebraic error. Then we use some nonlinear numeric optimization, like the Levenberg-Marquardt algorithm, to minimize the geometric error, reprojection error in our case. And because of the images and key point detection and matching, there can be noise. So we use RenSec to robustify it. And on the GPU, we create the canvas where we will draw the images together. This is has a fixed aspect ratio, which resizes, so that's why we need the scale factor as well. Then on the fragment shader, we just work with and do the homogeneous projection with this function built into OpenGL. So it's quite simple, but quite effective. And some interesting facts as well, because as you can see here, these cameras are rotated around the common axis. So we can leverage that to rotate the panorama. This can be good if the perspective projection is too large on the side images, and we can minimize distortion that way. And we do this by getting the rotation out of the homography between two images. This can be selected freely, but we use the middle two images. And then we can get an axis and angle representation from that. And if we change the angle and put everything back together, everything will rotate. So we only need to change one matrix per rotation, per whole panorama rotation. So to formalize it a bit more, as I said, this is the homography, which is the same as was in the previous slide. And we can write a point registration problem. Like we want to, so if we want to see the column vectors of this matrix, then we will want to map it to the column vectors of these with a rotation. And it's non-trivial because this is an orthogonal matrix as well. But with the help of Aaron et al. His method, then we can optimally estimate this rotation. So for the point cloud colorings, we draw them as particles, simple as that, one draw call per frame. And we have currently 3 coloring schemes. One is based on reflection intensity, you can see it right here. Then we use the camera images to get the real color of the points and color the ground plane as well. For the first one, this reflection intensity comes from the LiDAR sensor itself, which is an integer value between 0 and 2055. 0 is basically a non-reflective, perfectly diffuse surface, and is a perfectly reflective surface. At least it tries to map these values to these properties. It's done in sensor as well, so we don't have control over it. And we colored this with the ValueView application's color scheme because that's the official software for Velodyne LiDARs, which we have. So it's easier to understand and interpret it for us. And it is done by linearly interpolating between 3 colors in each HSV color space. And in the vertex shader, we just do the projection to the screen with this virtual camera matrix. Then we filter out the crash measurements, and then we do the color space conversions, which are branchless, by the way, so they don't have any if statements, and then we linearly interpolate between the colors. For the next one, we use the intrinsic and extrinsic parameters to project the 3D points to the images, and then we sample the texture, and that way we can get the real colors. You can see this is at the northern building, the corner of it, and you can see it's perfectly colored. It depends on the quality of the calibration as well. And this is basically what I explained, that we just project onto the image and then sample the texture if it's in bounds. And for the ground plane, we do just plane fitting. We use some heuristics to filter out points that are not necessary for us. So, for example, below the car, these are the ones we are interested in. And we use principal component analysis to find the plane, which minimizes the geometrical error, which we like. And it's optimal. It's an optimal solution in the least square sense, because we represent the plane with a point on it and the normal vector, and the normal vector will be the least significant direction of these points. And this is also sensitive to noise, so we also robustify it with transect. So it gives a decent start. So this plane fitting is done on the CPU because we also assume that the ground won't move. The car will, but it's negligible because it's always under the LiDAR scanner. And we also need a plane, so we can't do anything else now. Any defects on the roads, and we don't want to. And we just send the threshold, inlier threshold, and we color the inliers with red and the others gray. And the next interesting part is using map data to render around the vehicle. So we use the GPS coordinates to position the vehicle. That's also trivial, and we use map data from OpenStreetMap, and we process it, get the points out of it, and then render the roads with the correct color and width. And we also need to rotate the map around the vehicle because the coordinate system is fixed to the car. So we calculate a heading, which is the angle between true north and the direction of the vehicle. And we draw the roads. This is also really simple stuff. With instancing, each road is one draw call. And this is the instance geometry we use. And if we know these A and B points and the width, this also depends on what type of road, like a highway will be wider. And we transform it and draw them. So it's all done in shader. So on the CPU, we read in the map data, extract the points, extract the type, then we map bits and color to the types. Then we project the geodetic coordinates to UTM coordinates, which has north and east directions as basis vectors. So it forms an orthogonal basis band. It minimizes the projection error because it's each region on Earth has a different kind of band which we want to project to. And then we calculate also the heading here, and we send this information to the GPU. So on the vertex shader, we do this transformation of the road and road vertices, and then we give the final color in the fragment shader. So our future plans is to, it's already available for the public, this system and the data sets, but we want to move this project to GitLab to make contributions open as well. And we want to filter the position, GPS position, and the rotation, because it's quite bad if the vehicle moves slowly because the measurements are imprecise enough to affect the rotation. And we can use sensor fusion and the Kalman filter to account for this. And we would also like to use the Ackermann steering model. And we also have fisheye optics, but this program cannot handle it because sometimes most of the time the field of view is more than 180 degrees. Then this homography method won't work for the panorama, so we need a different kind of projection. So it's not handled yet. And we would also like the object detection in real time. We have some experiments with small YOLO model, and it works quite well, but it's not integrated to this application specifically. It's a different client. And we also want to record more data, especially with new weather conditions like big thunderstorms and such. And we have now snowy and footage with rainbows. That's quite nice. So in the future, no, this is the conclusion. Now it's available at this website. And I think I will want to demonstrate it because it's much more convincing to see it running. So. Okay. Yes, really nice. So we start the server application here, which will start to put everything to the shared memory in fixed time intervals. And then I will start the client itself, the client application. It will just calculate the homography and put the plane, and it will. Well, is it doing anything? Because it's yeah. So for the homography, sometimes it can be calculated right away because there is no data in the memory. Then we need to manually do this. Sorry if my laptop is slow, because if it's not plugged in, it's kind of a mess. So here you can see it in action. The rotation is a bit off. That's because of the measurements are all over the place. If the vehicle goes slowly, but if it speeds up better. And we can also rotate the panorama on the top. It's also a bit laggy because of the screen share, but now it's good. And I can just toggle the map to just show you the coloring schemes. This is the intensity one. You can see sometimes you can see the license plates of the cars with red. So detecting that is quite easy, both with the eye and both in code. The next one is the camera. It's a bit of gray area, so sorry. It's not the most colorful recording. And the next one is the ground plane. And you can recalculate it quite fast, so it also works in real time, both on the C. So you don't need to implement it on the GPU now because the point cloud is sparse enough that it works well. And here you can see that it's a lot better now, the rotation. So it's not doing that much flickering. So thank you for your attention.
Very much. And there is any question? Yes.
I assume that you are going to use it for autonomous driving.
Yes.
And
yes.
for this, I'm concerned, is the 4 FPS enough? Because at least from this demonstration, I'm not convinced that it's safe to use it.
Actually, my supervisor told that that first used this and they recorded it. I don't know why they chose that, so it's out of my control in that case. But yeah, it's true. Both the server and the client can work with faster FPS. Just it's the recording done with 4 samples per second. So if we want to speed it up, I can. It's just a parameter to rewrite in command line arguments in the server, and the client picks it up. And if you work up to 30 FPS correctly, because then reading memory that fast from SSD will overheat your laptop, and it's not that optimized yet, this server, because it's in C#, the client is in C++, so that's better.
Thank you.
Any other question?
Maybe I can have if no one has. So maybe just a very naive question. Could you use this technique to, for example, digitize the city to make some kind of digital twin?
Yeah, actually, maybe we will try to make an application with this that records signs on the road and put it to an OpenStreetMap, put it back to an OpenStreetMap format, and then we can upload it. And just by driving around, we can map the city. So that's quite nice. And maybe we will try to make some custom OpenStreetMap extensions to record, for example, road faults, because my other colleague works with 2D lidars and detecting defects on the road. So maybe that can be put into this as well. Yes,
That's very nice.
so that's flexible.
Thank you.
There is not any more question. Then let's thank again for the lecture. And let's jump to the next presenter, with Gergely.